Okay, so this problem is going to let us incorporate a lot of different ideas when it comes to analyzing electric circuits. And so we are going to look at combining resistors, we're going to look at total current, and we're going to use a little bit of Kirchoff's rules and, of course, Ohm's law. So the question is asking what is the current and voltage potential difference across each one of the resistors in this circuit. So whenever we're going to deal with a problem of this nature, we make a guess at which direction the current is flowing with a single battery in the circuit. And we are usually going to select that direction of the main current coming out of that battery, coming out of the positive and kind of heading out of the positive towards the negative. We do see a junction here, so we know that that current is going to have to split into what we will call I2 and I3. So we'll say that's I2 and that's I3. So that's one of the first steps you want to do when analyzing circuits. Now we have a number of branches, and so in our approach to reducing the circuit down to the base resistance, the most reduced circuit, we're going to take that approach first. Once we get the circuit all the way reduced, then we will look at Kirchoff's laws. Okay, so let's see if we can make this into a circuit that is only one resistor, one battery, and one current. So what do we notice? We have a collection of resistors in series. We have a number of resistors in parallel. So let's tackle those resistors in parallel first. We're going to combine to the equivalent resistance of these two resistors in parallel. And we remember that 1 over the total resistance of these two resistors in parallel is going to be equal to 1 over resistor 1 plus 1 over resistor 2. And so our 1 over the total resistance is going to equal 1 over resistor 1, which is 6 ohms, plus 1 over resistor 2, which is 12 ohms. And when we solve for that, we find that that total resistance is equal to 4 ohms. So 1 over 6 plus 1 over 12, and then of course take the inverse of that. So if I wanted to change this to an equivalent circuit, I would find that I still have my 18-volt battery. I've now combined these two resistors into a new equivalent resistance of 4 ohms. Then I have my 4 ohm resistor represented here and my 2 ohm resistor that remains there. So I'm going to do this stepwise. Then I see that I have resistors in series, and we know with resistors in series the total resistance is simply the sum of the resistors. So if this is resistor 1, 2, and 3 in this new resistance, then we add those two together, or those three together, and we get 4 plus 4, which is 8, and to our total resistance then is 10 ohms. So we're just adding all of those resistors together. That then gives me an equivalent circuit with 10 ohms of total resistance and 18 volts. So if this were my circuit, it would allow me to use Ohm's law then to determine the current right out of the battery, right at the location of the battery. So Ohm's law, remember, is V is equal to the current times the resistance. I want to solve for that current. So the voltage over the resistance is equal to my current. My voltage is 18 volts. My resistance is 10 ohms. And we find that the total current is 1.8 amps out of that battery. So we know that I1 is going to be 1.8 amps. So I'm going to erase some of this and go back to my original circuit so that we can now use some of the Kirchoff's rules to determine the voltage across each resistor and the current through each branch of my circuit. So we have I1, the current out of the battery, or from at the junction of the battery is 1.8 amps. All right, so now we're going to utilize some of the Kirchoff rules that we have learned. So keeping in mind that currents into a junction have to equal the currents out of that junction, and the net voltage across a loop is equal to 0. So we do have 3 currents, 1 junction here, and in that junction we know that I1 is going to equal to I2 plus I3. So that gives us our junction rule relationship, and there's the only one here. We would know I2 plus I3 would come together and equal I1 again, so it's the same equation. So then we want to start looking at our loops. All right, I have 1 loop that goes out of the battery, around, and back to the battery. I have 1 loop that goes out of the battery and all the way around, and then I have this little internal loop in that branch. So 3 possible loops for this circuit. So let's start with loop number 1. We'll call this loop A, loop B, and loop C. So remember, the idea behind solving a circuit problem in this way is that we kind of have a whole bunch of equations to work with until we have enough equations for the number of unknowns that we have. So far, in order for us to solve for I2 and I3, I need at least 2 more equations. All right, so let's look at the loop rule for loop A. So I'm going to start my loop coming across the battery. So that is going to be from the negative positive. That's 18 volts. Then I am going to go through this resistor. Current 2 is the current that is through that resistor. I'm going in the same direction as the current, so it is minus I2 times that resistance of 12 ohms. I then continue my loop. That loop is now in the direction of the current, but it's now current 1, so it's minus I1 times 4 ohms, and then it goes through I1 times 2 ohms. It also goes through that resistor. So that is 1 loop, and of course that loop is equal to 0. I'm going to simplify this equation. I have 18 minus 12 I2. These 2 can combine together, minus 6 I1 is equal to 0. So I have another equation that has I2 in it and I1, but I'm still not able to yet solve for I3. So that's 1 loop. Let's do another loop. We'll go loop B. That's this big one. So again, we're going to go through the battery. That's 18. We're now I3 is the current in this branch here. So I3 goes through in the direction that I am making my loop. So that's minus I3 times 6 ohms. I then come down and I'm back to I1 minus I1 times 4 minus I1 times 2, and that has to equal 0. So I go through the 4, I go through the 2 in the direction of the current I1, so they subtract. Simplifying this equation, I have 18 minus 6 I3 minus 6 I1 is equal to 0. I actually now have enough equations to solve my problem, but just to kind of rethink about those loops and practice, we do have this loop C. So we could also look at loop C. I don't need to. I have enough equations to solve the problem. 3 unknowns, 3 equations with those unknowns. But just to clarify loop C, I start here with I3. I am going with I3. And so I3 times the resistance of 6. It's in the direction of I3, so that is in the negative. That's minus. But now I'm going opposite the direction of I2, so it is plus I2 times 12, and that also is equal to 0. All right, so those are all of the possible equations. We have more than we need. All right, so let's start with this one. I have, if I kind of rewrite this over here, I have 18. I'm going to solve for I2. 18 minus 6 times I1 is equal to, I'm going to bring 12 to the other side, 12 times I2. I know that I1 was equal to 1.8 amps. So 6 times 1.8 is equal to 10.8. We have 18 minus 10.8 is equal to 12I2. And 18 minus 10.8, which of course is 7.2. Just confirming, so I'm always a little on the spot on screen. 7.2 then divided by 12 is equal to I2 is equal to 0.6 amps. So that is our current I2. All right, so we have the current of I1. We have the current of I2. We need the current of I3. I can use either equation to do that. I'm going to use equation C. It gets me there a little bit faster. We have I2 times 12, bringing this around, is equal to I3 times 6. I2, remember, was 0.6, so 0.6 times 12, well, that's going to be my 7.2. We already had that up there. 7.2 is equal to I3 times 6. We divide 7.2 by 6, and I3 is equal to 1.2 amps. All right, so we have the the current through the 6 ohm resistor, we defined as I3, that's 1.2 amps. The current through the 12 ohm resistor is I2, that was 0.6 amps. And the current through the 4 ohm and the 2 ohm resistor is I1, which we determined from our equivalent circuit as 1.8 amps. Excellent. So now it's a matter of, well, what are the voltages then across each one of these resistors? So we're going to look at, of course, Ohm's law to figure that out. Remember, Ohm's law is equal to Ohm's law is the voltage is equal to the current times the resistance. So our voltage of our 6 ohm resistor. So, let's do that a little different. The voltage of the 6 ohm resistor across the 6 ohm resistor, well, that is I3. I3 is 1.2 times my 6 ohms. The voltage across that resistor is 7.2 volts. The voltage across my 12 ohm resistor, that's I2 going across that. I2 is 0.6 times 12, and we get 7.2 volts. So across that resistor. The voltage across my 4 ohm resistor, that's I1 going across the 4 ohm resistor, that's 1.8 times 4, which is also 7.2 volts. It's very equivalent volt droppage. And then we have the voltage across the 2 ohm resistor, and that also is 1.8 times 2, which is 3.6 volts. So I have all 4 of my voltages across each one of those resistors. Again, this is the current through the 2 ohm resistor, and the current through the 4 ohm resistor is current 1. Current 2 is the current through the 12 ohm resistor, and current 3 is the current through the 6 ohm resistor. All right, so utilizing both Ohm's law, equivalent resistance, therefore an equivalent circuit, and then some of Kirchoff's rules. Good job.